Hello, and this is another part of the Math104 12550 Exam 2 review. So I'm Dr. Tatyana Khodorovskiy, and in this section of the Exam 2 review, I'm going to go through exponential and logarithmic functions. So first, a brief review on exponential functions. Exponential functions come in the form of a constant times a base to the power of an exponent. This is what distinguishes exponential functions from other functions. There is an x in the exponent, and the conditions is that a is not 0 and b has to be greater than 0. If it's the case that b is also greater than 1, then we have an exponential growth situation, and the graphs all look like this. So this is exponential growth. This is when money is accruing in a bank account with a certain percentage rate, when population grows exponentially. Another case that exponential functions model, when b is between 0 and 1, is the exponential decay situation. So this is a decay situation when something is exponentially decaying. For example, when a radioactive isotope is decomposing. In all of these cases, the exponential function have the same features, that its domain is negative infinity to infinity. Exponential functions are defined everywhere. Another feature is that there is a horizontal asymptote at y equals 0. Whether it's growth or it's decay, an exponential function is going to have its end behavior such that it tends towards 0. In an exponential decay situation, as x goes to infinity, f of x goes to 0. This is why we have the horizontal asymptote there. In the exponential growth situation, as x heads towards negative infinity, the function heads towards 0. It is also true that all exponential functions are always positive. So b to any x is always positive. Exponential functions can never be negative unless a is negative. So there's many applications of exponential functions. One application that we saw is compounding interest. There is two formulas for compounding interest. One is when we have the first formula is when we have a principal P, a rate R, time, usually given in years, T, and when we compound n times a year. So this is yearly rate, and this t is most often given to us in years. Then the compounding formula becomes as follows. P of t is the principal times 1 plus the rate expressed as a decimal divided by compounding n times a year to the power of n times t. And yes, you are responsible for remembering this. The second is when we have continuous compounding. When we have continuous compounding with the same P, R, and T as above, then the formula for continuous compounding becomes P of T is P e to the RT. E is Euler's number. It's a number with infinite amount of decimal places, that is 2.71. you should have it on your calculator. If you don't have it on your calculator, you can always just approximate this by putting in 2.71. So on the review, number 31 from the review tells us that we have $8,500 beginning in our account at the beginning of the year. We have a rate of 8.12%, an annual rate, and we're also told that we compound monthly. This is 12 times a year. And we're asked, what is the total worth? What is going to be the total worth in 20 years? So we use the first formula, and we just plug in. We plug in 20 for t. P is 8,500 times 1 plus the rate in decimal form. Over 12 to the power of 12 times 20, which is 240. So the numerator we have, in the exponent, we have n equals 12 and t equals 20. If we enter this into a calculator, then we have $42,888.18. What's most important is not the final number you get, but it is whether you use the correct formula and plug in correct things. So this was an example with compounding n times a year. Let me do another example. This is number 32 from the review, where we're asked to do the same thing, but with continuous compounding. We're told we have a principal of $10,500. We're told that the rate is 6.25%. And we're told that we are compounding continuously. When we compound continuously, we use the exponential function. And we're asked, what is the total worth of our investment in 25 years? So we use that second formula, and we plug in 25 in there. And this is going to be the principal amount times e to the 0.0625, the rate, expressed in decimal notation, times 25. We plug this into a calculator, we're going to get $50,092.70. Again, it's important that you use the correct formula and that you use it correctly. Next, we're going to do some graphing of exponential functions. And I already reviewed how the basic graphs of exponential functions look like, and you may also need to graph some exponential functions with some transformations that we learned in the first part of the course. So in question number 34, this is again 34 from the review, we're asked to graph the function f of x equals 3 to the negative x minus 2. So what we want to do is to first start out by graphing 3 to the negative x, and then I'm going to use a vertical shift, and I'm going to graph 3 to the minus x minus 2. Another important thing to remember is that 3 to the minus x is the same as 1/3 to the x. So this is the case where the base is between 0 and 1. This is a decay situation. So this function, if I'm just graphing 3 to the negative x, I'm going to have the following 2 points on it. I'm going to have the point -1, 3 and -2, 9. And once I have 2 points, I can effectively graph the exponential function. So this point on it, this is -2, 9, and another point on here, this is the point -1, 3. I also have a horizontal asymptote here of y equals 0. So now I'm going to graph the very same function, except I'm going to shift it. I'm going to vertically shift it 2 units down. And now in this vertical shift, my horizontal asymptote is now going to be y equals -2. In a vertical shift, the horizontal asymptote gets moved with the vertical shift. In a horizontal shift, the vertical asymptote gets moved. In a vertical shift, the horizontal asymptote gets moved. The same as with rational functions and their asymptotes. So this point, -2, -2, 9, is now the point -2, 7. And the point -1, 3 is the point -1, 1. And with a horizontal asymptote at y equals -2, my function becomes as follows. It will look like that. Again, when you graph, I want to see the basic features of an exponential function, that it's going to infinity fast on one side, it's going to 0 on the other side, or approaches a horizontal asymptote on one side, and try to plot at least 2 points of your graph. Next, we're going to look at logarithms. So a logarithm is another way of expressing an exponential. Recall that a logarithm, y equals log base b of x, is the same as saying b to the power of y equals x. This is the same information said in different ways. This is called the logarithmic form. And this is called the exponential form. We also have some basic properties of logarithms, and we are going to use them to solve some problems. So the basic properties of logarithms: first, a logarithm of base b of b is 1. This is the same in exponential form as saying b to the 1 is b. A second basic property of a logarithm is that log base b of 1 is 0. In exponential form, this is just saying that anything to the power of 0 is 1. And then you have the two properties which result in the fact that logarithms and exponentials are inverse functions of each other. If you plug in an exponential function of the same base inside of the logarithm, you're going to get back what you started with. Same thing, if you take a base to the power of log base b of x, you're going to get back x. So log base b of b to any power is going to equal x. Another way to think about it is when you're looking at the logarithmic expression, you're asking yourself, b to what power is going to give me x? And in property number 3, it's essentially a tautology. You're saying b to what power is going to give me b to the x? Well, the answer is x. And we're going to use these properties to do problem number 43. This is again problem 43 from the review. We're asked to use basic log properties to evaluate log of base 5 of 1 over 125. It's useful to know rules of exponents. This is log base 5 of 5 to the power of negative 3. Remember, 125 is 5 cubed. 1 over 125 is 5 to the power of negative 3. And so the final answer here is negative 3. 5 to what power is going to give me 1 over 125? And the answer is negative 3. Number 49, also from the review, asks us to use the log properties to evaluate the following. 4 to the power of log base 4 of pi. Now it doesn't matter that pi is there, anything can be there. Using property 4, we see that 4 to the power of log base 4 of anything is going to be that anything. And so the final answer is pi. Next, we're going to look at graphs of logarithmic functions. Just like the graphs of exponential functions, they're broken down into two cases, whether they correspond to exponential growth or exponential decay. So we're going to look at functions that look like log base b of x. And there's two cases. For all cases, b is greater than 0, just like b is greater than 0 for exponential functions. However, if b is also greater than 1, the graphs of the logarithms look like this. If b is between 0 and 1, the graphs look like this. In both cases, there is a vertical asymptote at y at x equals 0. In this case, this means that as x approaches 0 from the right, this little superscript plus means from the right, the function f of x goes to negative infinity. In this case, as x approaches 0 from the right, it cannot approach in the left, the logarithm doesn't exist there. F of x goes to infinity. So this is the end behavior described of logarithm functions, which we can get from the fact that its asymptote is x equals 0 and just how their graphs look. Another important feature of logarithmic functions is that unlike exponential functions, they're not defined everywhere. The domain of logarithm functions is only positive numbers, 0 to infinity. And they will have vertical asymptotes, vertical asymptote at x equals 0. So if we're asked to graph a logarithmic function like we are in number 51. In number 51 from the review, we're asked to graph the following logarithmic function. We're asked to graph natural log of x, x minus 4, of x minus 4. Now recall that ln of x is the natural logarithm. This is just log base e of x, where e is Euler's number, which is 2.71 ... So I'm going to graph this logarithmic function just similar to how I graphed that exponential function. There's a horizontal shift here. First I'm going to graph log of x, and then I'm going to use a horizontal shift to graph the function that we want, natural log of x minus 4. So the natural logarithm, the base is e is greater than 1. The graph of the natural logarithm is going to look like this. This point is 1, 0. Another point on this graph is going to be e, 1, because natural log of e is 1, natural log of 1 is 0. There's also a vertical asymptote here at x equals 0. Now if I'm going to do a horizontal shift 4 units to the right, the first thing that I want to put on my graph is that my vertical asymptote is also going to move 4 units to the right. So now I have a vertical asymptote of x equals 4. The function natural log of x is defined for all numbers that x is greater than 0. The function natural log of x minus 4 is defined for all numbers that are greater than 4. My point 1, 0 is going to move 4 units over to the right and is going to be 5, 0. My point e, 1 is going to move over 4 units to the right, and it's going to become e plus 4, 1. Whatever the number e plus 4 is, it's going to be 6.71 something something. And now I can graph how my function is going to look like, and it's going to go through these 2 points and behave like all log functions. Log functions will go towards infinity in both cases. So as x goes to infinity, natural log of x goes to infinity, and same is true of all log functions. Next, we're going to do some algebra exercises with other properties of logarithms before we just use basic properties of logarithms, but logarithms have more properties. In particular, they have the multiplicative property where they take products to sums. They have the quotient property where a logarithm takes a quotient to a difference. And there's the power property of logarithms, that a logarithm of anything to the power p is going to be p log of that something. So these are 3 other properties of logarithms: the multiplicative property, the division property, and the power property. And we're going to apply this to two examples. We can be asked to either expand, this is also problem number 57 from the review. We're asked to expand the logarithm, natural logarithm of the square root of b plus 1 over b minus 1. Now again, it's useful to know exponent rules with radicals. This is natural log of b plus 1 over b minus 1 to the power of 1/2. So what I'm first going to do here, I'm going to use the power rule. The power rule says that I can bring that 1/2 out front, and this is 1/2 times b plus 1 divided by b minus 1. Now I'm going to use the quotient rule to expand this further, and this is 1/2 times natural log of b plus 1 minus natural log of b minus 1. I can leave it like this, or I can distribute the 1/2. That doesn't matter, it's already expanded. What's important is that I cannot simplify log of b plus 1 or log of b minus 1 any further. Another application of these properties is we can be asked to rewrite an expanded logarithm expression as 1 log. So we can ask to take something like this, natural log of a minus 3 natural log of b minus 7 natural log of c, and rewrite as a single logarithm. So what I'm going to do first, I'm going to use the power rule. This is natural log of a minus natural log of b to the power of 3 minus natural log c to the power of 7. I can also switch the minuses to pluses, but then my exponents are going to be negative. Then I rewrite this as a single logarithm. But before I do that, I want to use each rule separately. I'm going to gather all the minus signs, all the logs with minus signs, and then I'm going to write them as follows. This is natural log of a minus natural log of b cubed times c to the 7. I just used the product rule, and now I can use the quotient rule, and my final answer is natural log of a divided by b cubed c to the 7. So if I want to write this expression as 1 logarithm, the answer is that this is natural log of a divided by b cubed over c to the 7. As a rule of thumb, everything that has negative signs is going to end up in the denominator. Everything that has a positive sign is going to end up in the numerator. Next, we're going to solve equations involving exponents and logarithms. Equations with exponents can basically be solved with two main strategies. One strategy is to put both sides over a common base and then match their exponents. Another strategy is to take logs of both sides. We're going to apply this in number 62, where we're asked to solve the following equation. 125 over 1 over 625 to the power of negative x negative 3 equals 5 cubed. Now a lot of things here seem to be powers of 5, so we're going to use strategy number 1 and rewrite everything as an exponential expression with base 5. So on top we have b cubed, 5 cubed. On the bottom we have 5 to the power of negative 4 to the power of negative x minus 3. And what makes this a exponential expression is that there's an x in the exponent. Now I can see I can divide both sides by 5 cubed. And this is 1 over 5 to the negative 4 to the negative x negative 3 equals 1. Next, the bottom, a power raised to a power gets multiplied. So this is 1 over 4x plus 12 equals 1. Multiply both sides by 5 to that exponent, and we get 1 equals 5 to the power of 4x plus 12. Now 1 is also 5 to the 0. This is 5 to the 0 equals 5 to the 4x plus 12. This means that 0 equals 4x plus 12, which also means that x equals negative 3 is our solution, and we can certainly plug that in to check. If we plug in x equals negative 3, the bottom becomes something to the power of 0, which is 1, and we have 125 equals to 5 cubed. We will use strategy 2 when we do applications of exponents later in this review. Next, we're going to do logarithmic equations. Equations with logarithms can be solved with a few strategies. One strategy is to rewrite in exponential form and then solve as you would an exponential equation. Strategy 2 is use the fact that log of b of something equals log of b of something else is the same as those somethings equal to each other. And part of using this strategy is you may need to use some log properties to get the equation into this form in the first place. And whenever you solve logarithmic equations, you always check your solutions by plugging back in. One catch with solving logarithmic equations with a bunch of algebraic manipulations is that you, by accident, may gather some extra solutions. And logarithms are only defined on positive numbers, so you always check any solution that you get by plugging it back into the logarithmic equation and verifying that it is indeed a valid solution. So we're going to do number 67 from the review. This is the following logarithmic equation. Log base 8 of 7 plus log base 8 of negative 4x equals log base 8 of 5. So we want to use strategy number 2. We want to write as one side as log base something equals log same base something else. But we first need to use the log properties to get the left-hand side as one term. So this becomes log 8 of negative 28x. I'm using the product rule for logarithms equals log base 8 of 5. Now I'm going to use the rule number 2. This is log base 8 of something equals log base 8 of something else. This must mean that negative 28x equals 5. This must mean that x equals negative 5 over 28. And I can check by plugging back in. The only place where there's an x here is in the second term, and that is true for all negative numbers. Log base 8 of negative 4 times any negative number will work. So this is the answer. This is the solution that solves this equation. As a last example in this section of the review, we're going to do applications of exponential equations. A classical application is trying to construct an exponential function where population is growing exponentially. In number 69, we're given that in the year 2000, town A had population of 5,000 people. We're going to call, for simplicity, we're going to call the year 2000 as time t equals 0. We're also given that in the year 2010, town A had grown to 6,500 people. Since this is 10 years after 2000, we're going to call this t equals 10. We are told that the population grows exponentially. And we are asked to find population in year 2030. By our count, the year 2030 is when t equals to 30. So we solve this in 2 steps. Step 1 is to find the growth constant. So all exponential functions, all exponential models are going to look like this. All exponential models start with some beginning population, and then we can model this with the exponential function e to the kt. If k is positive, this is a growth situation. If k is negative, this is a decay situation. So in the case of population here, we have a growth situation. Whenever we have money accruing in a bank account, that's also a growth. Whenever we have radioactive decay, that is K, whenever k is negative, whenever we have radioactive decay, like in radioactive decay, that is a decay situation. So step 1 is to find that k. So find k. K is the growth constant. So we find k by plugging in the 2 values that we know. Well, we know that in our function, we know that at the start, at t equals 0, f of 0 is 5,000. This already tells us that in our formula, a is going to equal to 5,000. We also know, we plug in 10, when t equals 10, our population is 6,500. So this must equal 5,000 e to the k times 10. We plug in 10 in our formula. It is always the case that a equals to f of 0. If the beginning where our population or money started with, if we plug in 0 into this exponential function, e to the 0 is 1, and so we're just left with a. So now I have an exponential equation. I have an equation that I need to solve. I have 6,500 equals to 5,000 times e to the k times 10. So first I divide both sides by 5,000. And I get some number equals to k times 10. And now I want to solve this equation with exponents. I want to solve for k. So I take logs of both sides. This is going to be natural log of 6,500 divided by 5,000 equals natural log of e to the k times 10. Now, using log rules, natural log of e to the k times 10 is just k times 10. So this becomes natural log of 6,500 divided by 5,000 equals k times 10. This gives me the following. And solving for k gives us k equals 1/10 natural log of 6,500 over 5,000. You would enter this number into your calculator. There's no other way to solve it. And you would get that k equals to 0.0262. And then your formula, the one that you're going to use to compute what the population is in the year 230, is going to be f of t, 5,000 e to the 0.0262 t. Let me write it again so it's a bit more clear. This is 5,000 e to the 0.0262 t. And then in step 2, you would plug in the year that you want to get the population for. So you would plug in t equals 30. So this is the function with 30 plugged in. F of 30 equals 5,000 e to 0.0262 times 30. And when you plug this into a calculator, you should get that the population is going to be 10,973 people. So this is applications of exponential equations. So in step 1, when you're solving something like this, is to first find the formula. You want to find the formula that will model the population for time t. And this is the formula that models the population. If you plug in any t value greater than 0, it's going to tell you what the population of town A was. This is f of t equals 5,000 times e to the k value of k times t. And then to answer the question of, well, when exactly is the population, what exactly is the population going to be in the year 2030? That is when you actually plug in 30 and get some value for population. Now always check your answer. Any application problem, always check your answer for reasonability. If you would have gotten that there was 300 people in the year 30, then something is wrong because that amount of people should increase and not decrease. So always check your answer for consistency. And this is it for the review on logs and exponential functions.